Let's go ahead and finish up our chapter 3 with graphing linear inequalities. A lot of the skills we used earlier with equations of lines also translate to inequalities. We're just adding in the inequality symbol instead of an equal sign. When we first learned about inequalities, we learned that multiple values satisfy an inequality. X could be all values less than 3, or greater than or equal to all values of -2. So how do we graph an infinite number of ordered pairs that can satisfy a linear inequality? Well, we do that by shading in the xy plane. Any linear inequality is defined by a line in the xy plane where we cut it in half. And each half, whichever half is going to be our solution set, depends on the inequality sign. So the first thing that we want to do is we want to write the linear inequality in slope-intercept form, similar to y equals mx plus b. If we have a less than or greater than sign, we're going to use a dashed or a dotted line as our boundary to indicate that the points on the line are not included in the solution set. However, if we do have a greater than or equal to or a less than or equal to, then we will use a solid line as our boundary to show that the points on the line are included. If y is greater than mx plus b, or greater than or equal to, we shade above the line. If y is less than or equal to mx plus b, we shade below the line. And you can see here a chart that shows some solutions. Our boundary line is the line y, or x plus y equals 3. And if we have these two inequalities that are shown, we would use a dotted line to indicate the boundary. Since we have x plus y is less than 3, that's all the points in the shaded region below our boundary line. If we had x plus y is greater than 3, it's all the points above the boundary line. And if we look at a few of these points, we can see why they do and do not satisfy each inequality. For example, if we take x plus y is less than 3, and a point that's within the shaded region, well, -5 plus -3 is -8, which is indeed less than 3. And so we see how this point satisfies the inequality. And the same holds true for any of these points inside this shaded region. If we take a point that's on the line, such as 2, 1, and I substitute it into my inequality, then we see that 3 is not less than 3, therefore it is not a solution, which is why we use the dotted line to indicate the solution set, the boundary. So any point on the line will not be a solution, any point in the shaded region will be. Now, if we adjusted this inequality to be less than or equal to, and we had less than or equal to, then we would use a solid line to represent the boundary, and then any point on that line would then become a solution to that system. So let's go ahead and graph and check to see some solutions. First thing we want to do is rewrite our inequality in slope-intercept form. So we will subtract 2x from both sides of our equation, or our inequality. -y is less than -2x plus 6. And then we divide all parts by -1. Now, this is important. Remember that when we divide by a negative value, we have to reverse the direction of the inequality sign. So now y is greater than 2x minus 6. So we'll graph this line the same way that we would graph y equals 2x minus 6. We start at our y-intercept of -6, and we use our slope of 2 in order to get our line. So here, and we'll try our best to get it as close as we can. And because y is greater than, not greater than or equal to, we have to use a dashed line for our boundary in both directions there. Then we want to consider the inequality symbol for the shading. Well, because y is greater than, then we want to shade above the line. So we'll take our shading and we'll indicate that this whole region is our solution set. So all of that is our solution. Now let's go ahead and check each of these points. So we'll go ahead and plot them. Negative 2, 5, 0, negative 6, and 5, 3. Negative 2, 5 is inside the shaded region, so it is a solution. 0, negative 6, while it is on the line, because the line is dotted, we know it is not a solution. And 5, 3 is outside of our shaded region, so it is not a solution. And something that would be a good idea is when we have a solution that's not on the line, what we want to do is substitute it into the inequality and check it, just to make sure that we did our shading correctly. So if we want to check, we could take our original equation and we could substitute it with negative 2 and 5 for x and y, and make sure that we do get a true statement. Since negative 9 is less than 6, we know that we have shaded correctly, and negative 2, 5 is indeed a solution, as well as any other point in the shaded region. Take a look at the next example. And what we're going to do is, it's already in slope-intercept form, but we can rewrite it into a much more readable format, where y is less than or equal to 3x, rather than 3x is greater than y. Same line. Starts on our origin with a y-intercept of 0, and we have a slope of 3. So we can go ahead and graph. Try our best to get as close as we can. Because y is greater than or equal to, we use a solid boundary line. Therefore, any point that is on that line will be a solution to our inequality. Then we need to consider the shading. Y is less than 3, so we shade below. Let's go ahead and plot some of these points. We have the point 1, 3, negative 2, negative 5, and 5, 0. 1, 3 is on our boundary line, and because it's less than or equal to when we have a solid boundary line, it is a solution. Negative 2, negative 5. Well, it looks like it's outside of our boundary line, and so we think it's not a solution, but we could always double check by substituting the value into the inequality. Negative 5 less than or equal to 3 times negative 2. Negative 5, is it less than or equal to negative 6? No, it is not. Therefore, it is not a solution, and we were correct. It's very close to our boundary line, but is not on our boundary line. And the point 50 is clearly within the shaded region, so it is a solution. And we can go ahead and double check again by substituting into our original equation. 0 is less than or equal to 3 times 5. 0 is less than or equal to 15, therefore it is a solution, and we can verify it.